To demonstrate how to find the unknown constants for an initial value problem, I would like to consider the following third-order differential equation. The third-order differential equation given is y triple prime plus 3y squared plus 4y prime plus 12y is equal to 0. The first thing I'd like to do is verify the general solution of this differential equation. Because it is a third-order differential equation, the general solution is going to have three unknown constants. They come to us in the form of c1, c2, and c3, being multiplied to the functions e to the negative 3x, the cosine of 2x, and the sine of 2x. So to verify our solution, the first thing we'll need to do is take three derivatives. So we'll start with c1 e to the negative 3x, c2 cosine of 2x, and c3 times the sine of 2x. Let's start by taking a first derivative. The chain rule is going to be in play for all three of these. For the first one, this will be negative 3 c1 e to the negative 3x. Derivative of cosine is negative sine, and the chain rule gives us an extra factor of 2. So that'll be minus 2 c2 times the sine of 2x. And similar to the last one, this one will be 2 times c3 times the cosine of 2x. For the second derivative, chain rule will still be in play. Multiplying by an extra factor of negative 3, this will be 9 c1 e to the negative 3x. We'll get an extra factor of 2 here, so this will be minus 4 c2 times the cosine of 2x. Derivative of cosine is negative sine, so we'll see negative 4 c3 sine of 2x. And one more derivative to get to our third order. Extra factor of negative 3, that'll be negative 27 c1 e to the negative 3x. Derivative of cosine is negative sine, changing this back into positive 8 c2 sine of 2x. Derivative of sine is positive cosine, negative stays negative, so that'll be negative 8 c3 times the cosine of 2x. Now we get to take all of these and plug it into the original differential equation, and we'll see what happens. Sorry, the original differential equation. Let's go ahead and copy that down. Y triple prime plus 3y double prime plus 4y prime plus 12y. Well, let's plug them in. This will be equal to y triple prime, negative 27 c1 e to the negative 3x, plus 8 c2 times the sine of 2x, minus 8 c3 cosine of 2x, plus 3 times y double prime. We'll just go ahead and do that down on the next line. Plus 3 times 9 c1 e to the negative 3x minus 4 c2 cosine of 2x minus 4 c3 sine of 2x plus 4 times y prime. Y prime we got back here at this line. That'll be negative 3 c1 e to the negative 3x minus 2 c2 times the sine of 2x plus 2 c3 times the cosine of 2x. And then finally plus 12 times the original function. 12 times the original function, that is c1 e to the negative 3x plus c2 cosine of 2x plus c3 times the sine of 2x. Then we get to simplify all this. That should be fun. So my recommendation is to turn this into the three different kinds of functions that we see here, and then just sort of factor that out and take a look at all the coefficients that we get. So we are going to see e to the negative 3x times a whole bunch of things. We'll also have the sine of 2x times a whole bunch of things. We'll also see the cosine of 2x times a whole bunch of things. So taking a look at all of our e to the negative 3x's, I see one here, 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 and here. So in this step, I'm going to be distributing the coefficients and then writing them all down in here. So we have negative 27c1 from the first term. Then we have plus 3 times 9 times c1, so that'll be plus 27c1. Then we have 4 times negative 3c1, that'll be minus 12 times c1. And then we have plus 12 times c1. Good news there is that it looks like everything's going to wind up canceling out. As far as the sine of 2x, we're going to switch it over to purple for the sine of 2x. We have this one here, this one here, this one here, and this one here. So for our first one, that's 8c2, 8c2. For the second one, I am seeing plus 3 times negative 4 times c3. So that'll be minus 12c3. In the next line down, we have plus 4 times negative 2c2. That'll be minus 8c2. And in the last line, we have plus 12 times c3. Plus 12c3. Good news there. Looks like everything is once again going to cancel out. And we'll go ahead and switch over to green for the cosines. So I'll get a cosine here, cosine here, cosine here, cosine here. From the top line, we have negative 8c3. Then we have plus 3 times negative 4c2. That'll be minus 12c2. From the third line, plus 4 times positive 2c3. So that'll be plus 8c3. And then plus 12 times c2. So plus 12 times c2. And finally, if we take a look at all of the like terms that we have in here, negative 27c1 plus 27c1 minus 12c1 plus 12c1, those all cancel. We got 8c2 minus 8c2 plus 12c3 minus 12c3, those all cancel. Minus 8c3 plus 8c3 plus 12c2 minus 12c2. Everything cancels out and we wind up with 0. That is good news. Now that's also only half the battle because we haven't actually solved for any of these unknown constants yet. We've only verified that this is, in fact, the general solution. So now we get to the fun stuff. Now that we've done all that, I would like to find the solution of y triple prime plus 3y double prime plus 4y prime plus 12y is equal to 0, subject to these three initial conditions. Y of 0 is equal to 1, y prime of 0 is equal to negative 3, and y double prime of 0 is equal to 19. The good news is we just found all of these derivatives, so the general solution was c1 e to the negative 3x plus c2 times the cosine of 2x plus c3 times the sine of 2x. The initial condition that we have says that if I plug in x equals 0, I'm going to get y is equal to 1. So plugging in that initial condition will give me 1 is equal to c1 e to the 0 plus c2 cosine of 0 plus c3 times the sine of 0. So that simplifies to be simply 1 is equal to c1 plus c2. E to the 0 is 1, cosine of 0 is 1, sine of 0 is 0. For the first derivative from the previous page, that was negative 3c1 minus 2c2 sine of 2x plus 2c3 cosine of 2x. If we plug in this initial condition, that tells us that when x is equal to 0, the derivative will be negative 3. This gives us negative 3 is equal to, wait, I feel like I'm missing something. Yep, e to the negative 3x right there. So plugging in x equals 0, this will be negative 3 c1 e to the 0 minus 2 c2 times the sine of 0 plus 2 c3 times the cosine of 0, which is a fancy way of saying this is negative 3 is equal to negative 3c1 plus 2c3. That gives us a second equation in terms of the unknown constants c1, c2, and c3. Finally, for y double prime, this was equal to 9c1 e to the negative 3x minus 4c2 cosine of 2x minus 4c3 times the sine of 2x. Now, the third initial condition tells us that if we plug in x equals 0, we're going to get that the second derivative is equal to 19. I'll make sure we have enough space for this. So this will be 19 is equal to 9c1 e to the 0 minus 4c2 cosine of 0 minus 4c3 sine of 0, which is a fancy way of saying that 19 is equal to 9c1 minus 4c2. So what results is a system of three equations with three variables that we can proceed to solve for c1, c2, and c3. I'm going to start by using the first equation and the third equation that we set up, because those two equations only have c1 and c2 in them. I'm going to multiply the first equation by 4 and then add the two equations together. This technique is referred to as elimination addition, and it should eliminate our c2 variable. So 4 times 1 added to 19 gives us 23. 4 times c1 added to 9c1, that'll be 13c1. And the c2's will cancel each other out. This will give us that c1 is equal to 23 over 13. I can then take this value for c1, plug it back into the first equation. Solving for c2, we get 1 minus c1, so 1 minus 23 over 13, which will give us negative 10 over 13, once you establish a common denominator. Then I can take our second equation from back up here, solve this for c3, and plug in the value of c1 to get our value for c3. So according to that equation, c3 would be equal to, I'd have to add 3c1 to both sides, and then divide both sides by 2. So 3 times 23/13 minus 3 all over 2. So if we factor out the 3, that'll be 23/13 minus 13/13, that's 10/13, 5/13, factor the 3 back in, that is 15/13. Boy, I hope I did that right. Yeah, I think we're good. Therefore, our particular solution of this initial value problem will be the following. This is y is equal to, heading back to the original function and plugging in our values of c1, c2, and c3. c1 is 23/13, and that was the coefficient of e to the negative 3x. c2 is negative 10/13, and that was the coefficient of the cosine of 2x. And then we had plus 15/13, that was the coefficient of the sine of 2x. This would be our particular solution with the given initial conditions.